it, but only one of the main problem, what a main limitation is, it is having uneven distribution of solar radiation data. So because of sometimes sometimes actually this solar radiation, it is actually we are not getting because of the cloud. Hello, sir.
Sir, you can continue.
Okay. Some because of the cloudy nature, this solar radiation, it is not actually getting up to the mark, and it is in distribution nature. And morning time we are getting the very less solar radiation data, and mid of the day we are getting more amount of solar radiation data. At the end of the day, we are getting very less amount of solar radiation data. So it is not in the it is not continuous form. It is in distribution nature. And also in the night time we are not getting any solar radiation data. So if, because if you want to depend on the solar energy data, so obviously we need to store, either it may be electrical, either it may be thermal. So we know that if you use that solar PV panel, so we have an option like storage technologies. So we have a battery lithium, we have advanced materials also available, and lithium ion batteries are most promising technology nowadays, and we are storing that energy in the form of electrical energy. And what about the thermal? Suppose if you have, we have there are solar thermal systems like solar parabolic trough collectors, solar Fresnel collectors, and solar water heaters are available. So how we can get this thermal energy when we are not whenever we don't have any sun radiation data during the night time. So we have an option called thermal energy storage. So we have a different kinds of thermal energy storage systems are available. And first one is actually sensible heat storage systems. Second one actually is the latent heat thermal energy storage system. And third one is actually thermochemical heat storage systems. So for what is the terminologies? First of all, we should understand about that. What actually this sensible heat storage? What actually this latent heat storage? For example, let us take a small ice. 1 kg of ice we are taking. So ice having initially temperature of minus 20 degrees. So that ice you are giving some heat. It is start rising up this temperature, and it reaching to 0 degrees temperature. So once it is got 0 degrees temperature, what actually ice will happen? It is absorb, keep on absorbing the heat, but at that isothermal condition, so it is changing its phase, but temperature it is not changing. Once if it is crossing that 0 degrees temperature, it is completely converted into phase transformation from solid to liquid. Then only you start rising the temperature. Until unless you're keep on heating that particle, so what will happen? Once it reaches that 100 degrees temperature, like boiling point temperature, so the temperature is maintained constant. So once it is keep on absorbing the heat, so your liquid particles will be slowly converted into vapor particle. Here the phase change will be happening. So once entire liquid particles will be converted into vapor state, now it is again start heating and changing its temperature. So now if you observe this trend from minus 20 to 0 degrees, you are heating. So it is temperature is changing, but temperature is changing and still it is absorbing heat. So that kind of what are the heat we are supplying that range. So that heat we call it as a sensible heat. Once it is reaching the isothermal condition, like let us take phase transformation temperatures like 0 degrees temperature and 100 degrees temperature. Here, these temperatures, actually the phase transformation will be happen. Here, the temperature is maintained constant, and but heat will be keep on absorbing. So by changing its phase, so those heats, whatever the heat we are supplying, that heat we call it as a latent heat. Okay, so using this phenomena, we can store the heat either in sensible form, either it in the latent form. Okay. Let us talk about sensible heat storage system. So sensible heat storage system very quite common. Like it is not that much complicated system. So let us take any concrete material, any sand particle material. I was generating higher temperature steam I'm generating. I want to store. So what I can do? So I can simply send this hot water or whatever it may be, either hot steam. I'm sending into the sensible heat storage system. So it will be absorbed in the sensible heat form. We know that. We know that sensible heat, it is nothing but MCP delta T. So sensible heat form will be nothing but Q is equal to MCP delta T. So here that what are the heat we are supplying, it will be mainly depends on the three parameters. One is the mass of the material, and second one is the specific heat capacity, and third one is the temperature difference. Suppose I want to fix the temperature difference, temperature gradient. In from, let us take, I want to store that hot water from 100 degrees to 150 degrees temperature range. So I'm sending this hot water. So what actually now this temperature gradient is fixed. So it is mainly depends on the only two parameters. Now what is the parameters? Specific heat and mass. Suppose if you selecting constant material, so I'm going with only concrete material. So now my CP value is also remains constant. So now it will be vary only on mass. It is mainly depends on the only mass. Suppose I want to store more amount of heat, I have to design with a higher mass. So the high bulky storage system have to maintain. Suppose I want to store 100 kilowatt. I want to store 100 kilowatt. So my system mass will be like 100 kgs or something like. Suppose I want to design for 200 kilowatt storage. So what I can do, I can improve, I can increase that mass. That is a main problem. So here, the sensible heat storage system, it is mainly depends on the temperature gradient and mass and specific heat. And let us consider, let us take, let us take another system, that is uh, thermochemical energy storage system. This is actually mainly having the two kinds of systems are available. That is solid to gas and liquid to gas, or gases phases systems will be there. So this concept is very simple. So suppose two particles are there. So suppose two materials are there. So two materials at certain temperature, these two materials are making some reaction. So making some reaction. So let us take one material like calcium chloride and water we are taking. So at 200 degrees temperature, you are heating these two materials. So these are combined together and making some new solution. So calcium hydroxide something material it is forming. And if you doing the reverse process, if you're doing some reverse process, this product will be splitted into same component, and what are the heat you are supplying, same amount of heat will be releasing up. So that's a this kind of systems are, we call it as a so thermochemical storage system. So two products are combined together at particular temperature. When the byproduct are recombined together, so same amount, what are the heat you are supplying, same amount of heat will be released. So this is also very famous technology. So thermochemical is, so energy will be stored in the form of chemical energy. And so there is some limitations are available for this thermochemical energy source system. Why? Because this is very, it is not that much popular. It is still in laboratory scale only. And as compared to that lifespan, so sensible heat storage system. So let us take sensible heat storage system having the highest lifespan, like to up to 20 years, 25 years, up to it you're having. Let us take, if you take that thermochemical energy storage system, the lifespan it is very less only, so below 2 years only. So that is the main limitation. But one of the biggest advantage of this thermochemical energy storage system is like we can give more amount of heat. So we can store more amount of heat per area, so we can store more energy. That is possible as compared to the remaining technology. So because of these limitations, because of these limitations, like storage technology is not adaptive, and one more thing, like chemicals also so expensive, and lifespan also very limited. So because of these limitations, so people are moving with that another technologies, that is uh, latent heat thermal energy storage system. So this is the classification. Thermal energy storage system will be classified in the physical form and chemical form. In the chemical form, it is mainly having a thermochemical energy storage system. In the physical form, we have uh, a sensible heat storage system and latent heat storage system. In the sensible heat storage system, again, it will be classified into two ways. One is that solid and liquid. So solid means like only solid particles we are taking, like sand particles, concrete particles, or any metals we can take, any alloys we can take. So that will be only like say only one single phase only it will be having. So whatever the heat we are giving, so the phase cannot be changed. Only temperature only will be varying. So that is a sensible heat storage system. Let us suppose some if you take the material like liquid materials. So even liquid material also having some sensible heat capacity. Like let us take the water. So what is the best example? You want to heat the water from 20 degrees to 60 degrees temperature. That heat will what are the heat will be stored so that we can call it as a sensible heat storage. And some kind of salt particles and some kind of thermal oils. So that is also let us take one oil you are heating up. So it will be heat will be absorbed. So after some period of time, slowly the heat will be dissipated to the outside. So
ఇద్దరు
similarly, heat will be
అదేలే
heat
నాకు
will
రాదు.
be
నేను కనుక్కొని నేను నీకు చెప్తానులే.
uh, similarly heat will be stored. Coming to that latent heat storage technology, so I already told that. So whenever the phase change will be happen, so whenever the heat will be observed, so the phase will be varying. It may be varied from solid to gaseous state. Either it may be vary from solid to liquids, and it may be varied from liquid to gas, and sometimes the solid to solid particles. So we have four combinations are available, but mostly whenever the gases parts are involved, we can skip it. So why? Because suppose you want to store the heat. Whenever you want to store the heat, suppose I have a 10 kg, I have a 10 kg mass of I have a 10 kg mass of storage material. When it is this initially it was in solid state only. This solid material, this 10 kg having some volume. Let us take the volume. It may be 10 liters. Let us take. So whenever it is converted into vapor state like gas state, the gas will be expanding more as compared to the solid particles. The gaseous particle having the more volume. So whenever you want to design the storage container, initially we are designing with the wholly less volume only. So when it is having expansion, the obviously expansion will be takes place. So more pressure will be built and the system will be explode. So that is a problem. So there are some problems with this uh, solid gas and liquid gas. So this kind of material we can skip it and we can move with that some other materials like that is called solid to liquid and solid to solid. So solid to liquid, let us take like paraffin wax. Let us take some very common passage material in candles and all we are using. So initially it is having solid state. Whenever you heating the temperature, you giving the temperature of 50 degrees temperature. So once it reaches the melting point temperature, that wax will be slowly converted into liquid. So after some period of time, it is what will happen. It is what are the stored amount of heat it will be released to the atmosphere, and it will again become a solid state. So here, as compared to this gases part, so the solid liquid phenomena if you're applying, so it is somehow little bit adaptable. Why? Because the volumetric expansion of the liquid is not that much high as compared to the gases part. So this is somehow little bit good. And another particles also there, another materials also there, that is like solid to solid. So what are the heat we are giving here, the phase cannot be changed, but it will be converted into one form to another form. That will be possible. So like one transformation to another transformation. Suppose initially the solid particle having the alpha transformation, and if you heat that material, it will be converted into beta transformation. So here the transformation will be done. So whenever you are releasing the heat, so that same it will be get back. It will be coming to the get back. So that will be
तो टीचर ने
happen.
यहाँ पे लिखा था टीचर को 100% पता था क्योंकि टीचर ने उसको देखा को देखते हुए
Uh,
इसके बीच में पीछे
So
जाके
majority of the PCMs are considered for thermal energy storage systems are solid to liquid phase change materials only. And again, these solid to liquid phase change materials are again classified into based on the temperature. We can classify that is low temperature applications. Uh, that is below 220 degrees temperature. What are the melting point temperature? What are the materials are there that you can take it as a low temperature application. Like example, paraffin wax and some kind of salts will be there. And suppose if you the temperature, melting point temperature, which is in the range of 220 to 420 degrees temperature range. So those kind of materials we comes under intermediate temperature applications. So like solar, this is basically these kind of materials will be useful for storing of medium temperature like solar steam. Solar heat, it is generating some heat. So that heat we can store with in this particular temperature range. Let us take high temperature application. So superheated steams and you are generating from the solar thermal collectors. So mostly these superheated steam temperature having higher temperature, that is around 420 degrees temperature. That will be stored with the help of this PCM material. So for your understanding, I'm simply say that phase change material, the name itself indicates that phase change will occur. Phase change will occur at particular temperature. Any material, guys, some disturbance are coming. So can you mute your voice? Okay, so any material which is changing its phase from one temperature at constant temperature, those kind of material we can call it as a phase change material. Let us take aluminum. So aluminum actually solid state. At 800 degrees temperature, what will happen? It will be converted into liquid state. So solid to liquid. So aluminum is also one of the best example for phase change material. Any material which is changing its phase, that material we call it as a phase change material. So this is the somehow as compared to that durability, sensible solar system having the more lifespan around 20 years. If it is take the latent heat storage material, it is having the durability is around 5 years, and chemical energy storage system very less very less span of time. But commercially, most available materials are sensible storage materials, and somehow latent heat storage materials also available. But chemical energy storage materials are still, it is under research only. It is not as of now. It is not commercialized. There is some practical difficulties are there. And compared to that, all the systems, so chemical energy storage system having the more storage density. So at small mass itself, it can able to store the more amount of heat. But coming to that latent heat is also, this is also somehow a little bit higher energy storage density. But least energy storage density materials are sensible heat only. So single phase only, obviously it is not absorb that much heat. But whenever the phase change will be happen, they're only having the more amount of heat will be transferred. So that is basic thermodynamic principles. So we have a different types of phase change materials. So that is organic phase change material and inorganic phase change material. So what is the difference between organic and inorganic? So organic materials are nothing but one of the material compound structure. It is having that carbon and hydrogen chain bond will be there. Those kind of material we can call it as a organic phase change material. Like, so let us take some sugar alcohols. Sugar alcohols is nothing but like glucose material. So that is also like, if you take that sugar. So sugar is also one of the best example for the phase change material. It is a glucose form. It is having the structure of carbon, hydrogen, and oxygen, and there is no extra components are there. And if you take that paraffin wax, so paraffin wax actually it is having that chemical structure of carbon and hydrogen only. So the who are the materials having the carbon and hydrogen bonding structure, those material we can call it as a organic phase change material. And coming to that inorganic phase change material, salt kind of material, let us take, so any salt kind of material if we take, so those materials we can call it as a inorganic phase change material. So what are the advantages and disadvantages of organic phase change materials? Uh, the main advantage of organic phase change materials are it is having the best less supercooling and subcooling values. Let us take what is actually this supercooling and subcooling terminology. So suppose I have one material, the material having that a melting point temperature at 30 degrees. So if you give the heat at 30 degrees temperature, the PCM was melted. So whenever you want to extract the heat. So whenever it releasing the heat, what are the stored heat, it is releasing the at same 30 degrees temperature. It never be happen. Some difference will be occurred. It may be released that at 25 degrees temperature. Some that deviation will be there. So that 5 degrees temperature deviation, we can call it as a supercooling. So supercooling is actually very less for this kind of material. That is the main advantages, and it is ability to be incorporated directly. So mostly these organic wastage materials are carbon hydrogen structures only. So this is not like salty materials. So you can store at anywhere. So any kind, it will be compatible with the any material. Like if you want to store in the steel, it can be easily adaptable. And if you want to store the heat in like copper also, that is also possible. So corrosion will be very less for this kind of organic wastage material. But if you go with that inorganic wastage material, so salts and all, it is highly corrode that material. So there is a practically some difficulties are there with whenever using with inorganic wastage material. And it is having a good thermal performance and compatible with any conventional material. Already told, any material we can store, chemically stable. Even if you keep on heating and cooling, so if you perform the thermal cycles, like after some cycles also, it is chemical structure never be changed. So that is the best example, best advantages. And higher heat of fusion, so delta H value. So at more amount of heat can able to store. That is the best thing. And safe and non-reactive, and it will be easily recyclable. These are the some of the advantages of organic wastage material. Coming to that disadvantages, so it is having that low thermal conductivity. So that is one of the major drawback. Not only this organic wastage material, any materials, any wastage material having the less thermal conductivity. So whenever you want to use these materials in real-time application for thermal energy storage system, the material must be having the higher thermal conductivity. That we have to ensure it. So that is important. And it is organic facial metal, mostly it is burnable, so it easily catch the fire. So that is a main disadvantages. And it is also low phase change enthalpies value it is having, and low density, and requires large surface area whenever you want to use it. That is one of the disadvantages. And flammable and more expensive, and high volumetric expansion will be takes place, and low heat capacity. These are the some of the disadvantages of the organic wastage material. And inorganic, coming to that inorganic wastage material, as compared to that organic wastage material, here the thermal conductivity somehow higher. But even inorganic wastage materials also most challenging part is lower thermal conductivity. So, but compared to the organic wastage material, this inorganic wastage material having the more thermal conductivity. And it is also compared to that organic wastage material, this inorganic wastage material having the large heat storage capacity. This is the one of the main advantages. And it is lower volumetric expansion, even whenever it is phase is changed from solid to liquid state. So it not occupy that much volume, so very less variation of volume will be happening. And even less costly. Even salts or organic wastage material having the higher cost, but these salty materials actually it is very cheap in cost. And it is non-flammable, it is not catch the fire. And sharp phase change. So sharp phase change means, suppose the material having a melting point temperature around 30 degrees, whenever it discharging that heat at same temperature, it will be happening. So that is actually happening. uh, and so greater phase change enthalpies, and this is also kind recyclable materials. So what are the disadvantages of this inorganic phase change materials are like lack of thermal, high degree of supercooling, like I already told. So supercooling, it is a deviation between the charging to discharging, or that temperature difference. We call it as a supercooling. So that will be very high for that inorganic phase change material. And thermal stability, lack of thermal stability. So that means if you keep on heating and cooling, suppose I want to store the heat. You are storing the heat. It is absorbing the heat. Whenever it releasing heat, it releasing. So one cycle will complete. So how many times you want to store heat? How many times you want to release the heat? So here you have to perform different kind of cycle. Similarly, in the battery also, what actually battery will do? So you are charging and discharging, charging and discharging. Similarly, here also you are giving the heat, it is charging. You are retrieving the heat, that is discharging. So here more number of times you are performing, it will affect the properties of the phase change materials. So that means the latent heat value will be reducing. That is the main disadvantages for that inorganic phase change material. It is little bit weight as compared to that organic phase change material, and it is also having corrosive nature, and phase aggregation will be happen. So phase aggregation means whenever it is releasing the heat, it has to be come back to the solid state. But sometimes it is not fully completed into solid state. Some liquid particles will be left over. So some phase aggregation will be happen. So that is what actually happened, and prone to degradation. So chemically, sometimes it is not stabilized. So after some frequent thermal cycle, so the chemical structure will be changed. So the degradation will be happen, and chemical instability will be happening. And compatibility issues with metals. Suppose salts, I already told, salts are actually you want to store in the any material like copper if you want to store in the copper, and the copper actually it will easily corroded because of these you want to put in the salt. So whenever you want to store the salty material, obviously that will be affect the metals. So because of corrosive nature. So that's why these inorganic materials are corrosive in nature for with metals, and requires containers and supports. So special kind of containers we have to design for this inorganic phase change material. And coming to that, in- another classification, that is eutectic. So here eutectic materials are like it's a combination, like it's a combination of any material, like organic to organic and inorganic to inorganic, and sometimes organic inorganic combination. Let us take this. This is actually these kind of materials we can call it as a eutectic material. So like binary mixing. So you can combine two materials and make new component. That is what you call eutectic. So the advantage of these eutectic materials are sharp melting temperature and high volumetric thermal storage density, and no phase aggregation will be happen. These are the main advantages. And coming to the disadvantages, this is not actually nowadays. Actually, these are in the research state only, and we have a limited information are available. So suppose I want to mix some salt with some paraffin bags. So I want to make some new component. So here if you vary the proportion, suppose paraffin bags are mixing with 40% and salt are mixing with 60%. This 40:60 ratio, the new component, how it will behave also we don't know. So and suppose you want to vary the proportions like 30% to 70%. So that combination of how the properties are vary also we don't know. So there is a lack of information are available for this eutectic phase change material, and it also suffers from supercooling, and it is also having a lower latent heat value. These are the some of the drawbacks of the eutectic phase change material. Now coming to the phase change materials, so the main limitation for the phase change material was leakage and the lower thermal conductivity. These are the major problems in the phase change material. So mostly latent heat thermal energy storage system, we are using solid to liquid phase change material. So that means solid, and it will be converted into liquid phase. So when it is converted to liquid phase, it has to be leaked out. It has to be leaked out. So that is a problem. So when you are using in real-time application, so suppose I want to put this phase change material in any application, what will happen? It will be leaked out. So it will be converted to liquid state. Obviously, it will be leaked out. So that you want to arrest that leakage, and you want to improve the thermal conductivity. So I already told the major problem with the phase change materials are lower thermal conductivity. So we need to improve the thermal conductivity, and meanwhile we need to arrest the leakage issue. So that can be possible with the help of this kind of techniques. Either we can put that some kind of pin kind of structure we can use, or else we can do some encapsulation, like we can cover the phase change metal with some kind of metals or some kind of inorganic materials, So that encapsulation we can do. So, drugs and all what you can do. So medicine will be kept inside that some shell kind of material will be same kind of technology we can adopt into that encapsulation of materials. And also like we can disperse some nanoparticles, nanoparticles. Let us take high thermal conductive nanoparticles like copper nanoparticle, copper oxide, silver oxide, and some carbon based nowadays most popular nanoparticles are carbon based structures, so like carbon multi-wall carbon nanotubes and graphene and silver nanoparticles. If you mix to the phase change material, so that we can obviously improve that thermal conductivity. That is possibility. You see, you can addition the nanoparticles. So, high carbon nanotubes, graphene, and silver nano. These are actually high thermal conductive nanoparticle. If you mix these particles to the phase change material, obviously the thermal conductivity will be improved. That is the one advantage. But thermal conductivity will be improved, but leakage was not arrested. That is a problem with this nano-based phase change material. But how we can improve the thermal conductivity, and meanwhile how we can improve the say leakage, how we can arrest the leakage problem? That can be possible if you put this materials, phase change materials into the porous structured material. So you see, this kind of materials we can call it as a porous structure, like spongy materials. So metal foams, copper foam, we have some expanded graphite. This is also kind of porous structured material. So these materials, if you put it into the phase change material, so what will happen? Even it is, if you are heating, it will be converted into liquid state. So, but even it is converted to liquid state, but these liquid materials are stuck in this pores, and it is not leaked out. So that's why these porous structured materials are very famous materials. So we can arrest the leakage issue, and these are actually expanded graphite. If you take graphite, actually like carbon material, so having the high thermal conductivity, and metals also have the high thermal conductivity. So we can sort out the thermal conductivity problem, and that also we can able to arrest the leakage issue also. So simply, for example, let us take the sponge material. If you put the sponge in the water, what will happen? So the water will be stocked in the pores of the sponge. So same kind it will be happen in the here also. So if you make this kind of material, if even after heating also the liquid particles are try to leak it out, but because of these pores, it is stuck here itself. So obviously we can arrest the leakage issue, and we can improve the thermal conductivity. And another thing, and another technique is encapsulation. Another technique was encapsulation technique. So in this encapsulation technique, I already told the material was inside only. The core material was PCM material only, but outside shell it may be of any organic material like sometimes silica based material, titanium based material, or like it is like some kind of metal materials are available. So it is PCM was completely enclosed with the shell material. So if you are heating, what will happen? The material inside the PCM was converted into liquid, but it is not leaked out. Why? Because that shell was completely locked. The shell was completely locked the liquid phase material. So, but even this, so we can arrest the leakage, and shell was made with that any organic material, or it may be made up of any metal at a metal sample, so that because of that here the thermal conductivity also high as compared to the PCM. So we can resolve the issues like thermal conductivity. We can resolve the issues like thermal conductivity, and also we can arrest the leakage problems also with the help of this technique, encapsulation technique. And there is some other materials also available like hexagonal boron nitrate and spongy graphene. This is also like porous structured material. We can mix this material into the liquid phase material to arrest the leakage problem. And these are the like various material. And so now, what actually this shape stabilized phase
అది
change material?
రాజా డాడీ ఫోటో అతికిచ్చి సైన్ చేసి పంపించాలి. ఎలా అవుతుంది అది? ఆ వర్డ్ డాక్ అది పీడిఎఫ్ దాంట్లో ఫోటో పెట్టి పెట్టాలి.
So now coming to that shape stabilized phase change material. So in this shape stabilized phase change materials, actually we can you want to arrest the leakage problem, and meanwhile you want to improve the thermal conductivity. So we already discussed encapsulation is the one of the best technique, and another best technique is porous based material. So we can put that hello porous structured material porous structured material. So if you put that liquid phase change material, so the liquid materials are locked into that porous structured material. It is not leaked out. So here also the shell material was covered completely phase change material. It is whenever it converted in liquid state, it is completely locked. So these kind of material, either encapsulated material or porous structure material, we can call it as a shape stabilized. So shape was not changed. So here the PCM shape also remains stable, and here facing here porous structured material also shape was remains stable. So these kind of materials we can call it as a shape stabilized phase change materials. Now uh, what are the applications of this wastage material? Now, nowadays actually, if you're using the batteries, so batteries is the major problem was, so it is at higher heating rates, sorry, higher charging rates, higher discharging rate, the battery got having the more temperature. Once it is reaching that standard point temperature, obviously it will be exploded. So that actually we already seen in previous years. So 2 years back, actually, some incidents are happened that Ola vehicles are got exploded because of that they are not properly thermally manage the vehicle. So when you are keeping charging, even mobile also. So if you take the small mobile, so that capacity was 20 watts only. But so nowadays we have a 120 watts, 80 watts chargers are also available. So suppose if you put this 80-watt mobile to your 20-watt mobiles, so because of higher charging rates, what will happen? Your battery got having higher temperature. It reached the high temperature. So because of that high temperature, if you are unable, if you are not able to control the temperature, you are not regulating this temperature. So it reaches that certain temperature and your battery got exploded. So for that, we need to provide that some cooling techniques. So so most you have a active cooling methods and passive cooling methods. So active cooling methods like you are putting some fans and all. So we can cool that lithium ion batteries, or we can cool the lead acid batteries. So simply you put the fan, and the air will be circulated and heat will be dissipated. So that is that air cooling technique. And if you use that liquid cooling, like you are circulating some water, you are circulating some liquid, any oils, and or you are circulating the oil or water, it will be capture the heat and heat will be dissipated. So that is actually active cooling method. So coming to the passive cooling method. So in the passive cooling method, you are not putting any energy sources. So here and all, we are using some external energy devices, but here and all, we are not giving energy sources. So simply you can put the phase change material. You can put the phase change material. So PCM will absorb the heat, and whenever you don't want heat, at that time it will release it. So that kind of things will do. So nowadays actually 3D printed phase change material will be useful for making these kind of molds. So these are the batteries, So these batteries you can make once you convert this phase change material into shape stabilized phase change material, like these molds. If you heat these molds, this is porous structured phase change material. Suppose you are heating. The entire material was locked. PCM was locked in the pores only, and is also PCM was absorbed the heat. So if the battery was heated up, the heat was absorbed by this phase change material and stored it until a certain period of time. After your working was done, your working period was done. So at the time, it released the heat to the atmosphere condition. So these kind of materials we can make either by using fused deposit modeling, printing models, or else laser centric technique also you can able to do it. So once the shape stabilized materials was prepared, so you can able to print these kind of materials easily. And most thing is that And nowadays, these kind of phase-change materials are using for the cooling of solar PV panels also. You know, PV panel actually standard operating temperature was 25 degrees only. So when you are heating up, when you are heating solar PV panel, like if you keep that solar PV panel into the atmosphere condition, so atmosphere sunny condition, so the surface temperature of the solar PV panel was raised up to 40 degrees and 50 degrees temperature also, it will be raised. So because of the ambient conditions. So it is because of the higher temperature, but actually in the 25 degrees temperature only, the cell will give the best performance. So let us take whenever you purchasing the solar PV panel at 25 degrees, they clearly mention that at 25 degrees temperature, it will give the highest efficiency. Once once it is crossed the 25 degrees temperature, once it is crossed the 25 degrees temperature, for every 1 degree rise, so efficiency will be lose by 0.5% efficiency. Suppose you have a PV panel efficiency of 20%. So solar PV panel temperature was raised to 50 degrees temperature. So 25 degrees temperature was raised. So around 12.5% efficiency will be coming down. So, so you have a maximum efficiency of 20%, and you are because of the high temperature, so you're losing 12.5%. You have only 8% efficiency. So if you cool this solar PV panel, so you can get the maximum efficiency. That is the advantages of cooling this solar PV panel. If you put that solar PV panel, if you put that phase change material behind the solar PV panel, so obviously whenever the surface temperature was rise, so the PCM will absorb this kind of heat generated by heat. So obviously that surface temperature of the PV panel was stable enough at a constant temperature. So this is the advantage of phase change material. So where actually these PCM will used. Suppose I cannot use the phase change material at every time at every climatic condition. So there is some certain limitations are there. Suppose the summer condition, my ambient temperature or more than 25 degrees temperature at the time, I cannot use this material. Sorry, I can. If it is temperature was more than 25 degrees temperature, then only I can use. And if it is the winter condition, if it is temperature is more than 25 degrees, then only the PCM requirement is there. And apart from that, if that my PCM melting temperature was in the range of 3 plus ambient temperature and 6 plus ambient temperature, then only your PCM will be effectively capture the heat. So this is the thumb rule for selection of the phase change material as per your climatic condition. Why? Because every location is ambient temperature is not constant enough. So in suppose if you go to the Tamil Nadu conditions, Tamil Nadu state having the more temperature. Suppose if you go to the northern states, so they are having the climatic conditions are very different. So they doesn't have any ambient temperature is more than 25 degrees. But if you go to the southern states, so these states having the higher ambient temperature. So at that climatic conditions only we can able to use that phase change material, and the material selection also we have to follow with this thumb rule. And how we can do so. So we are conducting some, we are preparing some material in our laboratory. So what actually we done, so we taking one solar PV panel, and we are taking another solar PV panel that we are connected to the heat sink. So this is the heat sink, and we have another combination, heat sink plus safe stabilized phase change material. So safe stabilized material already told, porous structured material. So here I am using the porous structured material is easy. So easy is nothing but expanded graphite. The PCM phase change material what I'm using here, polyethylene glycol. So if you make this material, so the after conducting this experiment, so as compared to that bare PV panel, so this panel having the higher temperature, higher surface temperature, and if you use this PCM material, so that is having the very less temperature as compared to the remaining phenomena. And because of the less surface temperature of the PV panel, my electrical efficiency of the PV panel was significantly, it is improved. So what you can do? So what is the scope for this material? What is the scope for this material is we can able to print material. So once you make that safe stabilized phase material, we can able to print the material with the help of laser sintering technique or the fuse deposition model. And you can, if you make this kind of materials, so if you incorporate in the PV panel, you can increase the efficiency, and also we can able to reduce the weight of the, you can able to reduce the weight and size of the system. So this is the fuse deposition modeling technique. So if you make the safe stabilized material, so that can be we can make that material we can pass into the any extruder. If you pass to any extruder, that wide structure will be formed. So if you make that wide structure, so that can be easily printable. So similar like polymers. So how you are going to print using the polymers, using fuse deposition modeling technique, FDM model. So how you can able to print same similar way, you can able to make the as a leak proof material that you can pass into that wire, and it can be easily printed. And for solar steel application also, sometimes we can use that phase change material. You know, this is that solar steel. What is the use of solar steel? You know, it is used for generating the desalinated water. So suppose this is a very simple working principle. Suppose if you're keeping the water here, you're keeping the water here, and the bottom actually one plate will be there. That is actually black color plate will be there. So if the sun radiation will be coming, it will be enter into here, and because of the blacky nature, what will happen? It is more absorption will be takes place, and the water will be evaporated. So here the impure water or salty water, whatever it may be, you are sending here, so that will be evaporated. So evaporated water only is stuck locked here. So here the covered with that glass sheet. So uh, here the condensation will be takes place. So liquid droplets will be slowly collected here. So likewise it will be happening. So we can collect the fresh water here. So this we can use for the drinking purpose. So if you use the PCM material here, suppose if you use the PCM material here, what will happen? So the so even night time also it is the what are the heat will be there in the morning time that will be stored in the PCM. Even night time also it will stored heat will be released here. So the water will be keep on evaporating, and it will be condensing and release the fresh water. So that is the advantage of using the phase change material in solar steels. So you see, so this is the what actually, if you, this is the common normal solar steel. If you put that phase change material, so heat will be stored in the PCM. So during the night time, during the night time, it release the heat. So it release the heat, because of that releasing the heat, still evaporation will be done. Still the evaporation will be done, and it will be condensed, and the water will be keep on releasing during the night time also. Even sun is not available, because of the stored heat that will be utilized in the sun in the night time also. So we can improve the productivity of the solar steel. That is the one of the advantages. And where actually this 3D print. So here also we can make these beds, 3D printed beds we can use, and we can put into the solar steel, and we can improve the productivity. And similarly, see these kind of PCM beds are we can use in the cooling applications also, cooling storage applications also. You know, cold storage application, how it will be work. Cold storage application, how it will be work. So if you put that refrigerant, if you put that PCM panels over here, so it will be energy will be stored in the cold form. So the PCMs not only higher temperature, it is not meant for only higher temperature. It is even lower temperature also we can use. Some kind of materials will be there that melting point around -20 degrees, -30 degrees. It will be converted into liquid state. So whenever that energy was there, so that it will be coolness will be provided, it will be circulated, cold air or water, maybe it will be circulated here. But whenever if you put that these PCM panels over here, what will happen? So whenever that suddenly there is a interruption will be created, so there is no power and all. At the time here that heat will be, what are the cold stored heat will be there, that will be released. It will be provide the coolingness to the entire container. So so we can improve that COP value. And we can use in the refrigeration systems also in the phase change material. And suppose basic working principle of refrigeration system is evaporator, compressor, condenser, and expansion devices. So how evaporator will work? So it will absorb the heat, it will be getting heated up. So the heated refrigerant, here actually liquid refrigerant will be circulated, it is absorb the heat, and the vapor refrigerant will be enter into the compressor. The compressor will compress the vapor refrigerant, and the temperature will be raised up, and the temperature, high temperature liquid vapor refrigerant will be enter into the condenser. So it will releasing the heat to outside, and finally it will be expansion will be takes place in the expansion one, and finally liquid refrigerant will be circulating. So this is the common basic principle of vapor compression refrigerant system. Suppose if you put passage material over after this compression, so what will happen? So it will absorb the heat. What are the heat we are absorbing from that? What are the high temperature uh, high temperature refrigerant, which is coming from the compressor, that will be cooled over here, and cold refrigerant will be sent to the condenser part, so that my condenser load will be reducing. Obviously, the COP value will be increasing. And similarly, if you put that phase change material after the condenser, so after the condenser, if you put after the condenser, it is really what are the some temperature will be there that will be absorbed, and it is liquefied earlier before enter into the expansion devices. So subcooling effect will be happen, so that my refrigerant effect will be increasing. So that will be enhance your COP value. So my coefficient of performance will be improved. Similarly, if you put that phase change material after the evaporator part, so after the evaporator part, what will happen? So here the compressor load will be reducing. So if you compressor load will be reducing, so here the vapor will be generating, so it will be cooled down. So again, the cold because of the less temperature. So the less temperature vapor will be entered in the compressor. So my compressor load will be reducing that. That will gives that energy efficiency. So if you put that phase change material at any of the location of basic VCR system, obviously that it will be improve the COP. So performance will be drastically improved. So what you can do, this if you make any of this, if you prepare this safe stabilized phase material, that printable material into that this refrigeration system, so that will be easy. That will improve the thermal energy management, and that will also improve that energy saving system and efficiency. And also we can able to design flexible designs also, customize, we can able to customize, and you can able to design the flexible designs also. And not only like these commercial applications, so sometimes for textile industries also we can able to use this wastage materials. For textile industries, how it will be affect? So you have a layers of fabrics. In between the fabrics, if you put that wastage material, so it will absorb the heat. So suppose I'm wearing some clothes, I'm working in the very harsh climatic conditions, I'm working in the summer conditions, in construction industries, or sometimes I'm working in the before the blast furnace. So a lot of heat will be releasing, so that heat will be absorbed by the human body, so you feel discomfort, and you feel like you obviously is more sweating will become. Suppose what you can do, if you put that passage material in between these fabrics, so it will what are the heat will be coming up, so that heat will be absorbed by the passage material. It is not allowing into the your body. It's not allowing into the body like that. So some PCM embedded jackets we can make it, so we can wear it this kind of material, and we can, so what are the heat it is coming, and it is not allowing into the your body, so you feel comfort. So for a very hot climatic condition, so this kind of materials are very popular. So how we can make, either by coating or lamination. So this is the technique, this is the PCM based foam we can generate, safe stabilized phase material. We can pass it over here, and we can pass the two fabric material, and we can press with the help of the high pressure rollers, and finally PCM based laminated fabric we can design. And there is a spinning technique also we can use. So the PCM materials are what are the encapsulated capsule PCM materials are injected over to the fabric material, and those kind of fabrics are directly we can use. You see, these are the 3D printed cloths, nowadays actually even cloths also they are used to printing the help of this 3D printing technology. So if you incorporate the face change material, so it is it is not only useful for wearing, and it is also useful for regulating that temperature. So body temperature will be regulated. So let us take. So likewise, we can able to, so have you seen this video? So likewise, we can able to print the fabric materials. So these kind of facial materials are injected over here, and we can able to print this PCM based cloths. So that can be easily wearable. So this is the somehow it then somehow is the most beneficial thing. And what is the scope for this 3D printable PCM cloths? So this is very smart fabrics for temperature regulation we can use, and somehow energy thermal energy storage is stored in the clothing, and customized and flexible designs we can do. So that is the scope. And medical textiles for temperature management. Suppose the patient's temperature it is changing. So we need to you have to maintain his temperature. So they have a special kind of cloths will be there. Instead of those cloths, if you provide this PCM based cloths, and if you provide this kind of cloths, obviously that patient temperature, body temperature will be regulated. And safety apparels for extreme environment condition, I already told, whenever the person is working in that very harsh climatic conditions. So yeah, if he wear that PCM based cloths, so obviously he can avoid the discomfort nature. And nowadays, actually, in that helmets also, PCMs are actually using. So if you wear that helmet, so a helmet is actually nowadays mandatory for safety purpose. But if you use that helmet, your body actually releasing some heat. So as per third law of thermodynamics, as per the third law of thermodynamics, what it states, absolute temperature. If any body above absolute temperature, any body is there, obviously it will emit the heat. Even my body, and even above 1 Kelvin temperature body also, it release some emissivity. So emissive power will be releasing up. So from your head also some heat will be releasing up. So if you put helmet, what will happen is the entire heat will be locked over that helmet. So because of the more amount of heat will be accumulated over the helmet, you feel that there's some discomfort. So more sweating will be happening. So if you put that PCM pads over here, so what are the heat will be releasing from your head, that will be absorbed by that your PCM material. So it will temperature will be regulated. So your body temperature will be maintained constant, and you feel comfort conditions. That is the advantage. So this kind of 3D printed faces material based materials also, nowadays it is printable. Helmets also printable. That printable materials are used for your safety purpose. So what is the scope? And when I'm using this 3D uh, PCM based 3D helmets, actually it will effectively regulate the temperature, and it will absorb that impact energy absorption. Like sudden, there is a sudden heat is exposed, so it can capture that heat, and it is not allowing into the your head. And the comfort and the extended wearability, and that is the one of the advantages of this one. And customized helmet designs we can able to design, and we can able to reduce the helmet weight, and we can have a more safety in extreme environmental conditions. So, and nowadays this facial material we are using in that building applications also. You know, if you put that facial material into the building construction material, so what are the heat it is coming? It is not, it is not allowing into the interior part. So mostly we are using the concrete material, and we are using the brick material, and this concrete and brick material having some thermal conductivity. So whenever that heat will be solar radiation will be there in the slabs and all above the slab, it is exposed to that solar radiation. It is absorb the heat, it is absorb the heat from the slab. Actually heat will be enter into the interior parts. So what will happen? So if you want to control this if you want to regulate this temperature, if you put the passage material over the slab, so it will absorb the heat in the during the morning time. What are the heat will be exposed, so that heat will be absorbed by the passage material, and it is stored in it. And during the night time, actually, it has to release the heat. So during the night time, actually, the climatic conditions are completely different. So at the time, you need more. You need to release the heat. At the time, what are the stored heat will be there, that will be released to the interior part. So you are maintaining the comfort level condition, so that we can avoid the dependency on the air conditioning systems. So we can do that some encapsulated material. So macro encapsulated material. Suppose we have a passage material. So those materials are encapsulated with the any materials like spherical balls. The spherical balls, you can put that passage material, and cylindrical structures we have. In the cylindrical structure, we put the passage material, and some cuboid structure. So these kind of macro encapsulated passage materials, if you put over this brick kind of material, if you put over this brick kind of material and encapsulated materials you have put into the plaster, uh, if you put like this, so during that morning time when it is exposing, so it is absorb the heat, and it is stored in it, and it is not release, it is stored in it, and it is not allowing the heat to the interior parts. And nowadays, 3D printed materials are 3D buildings are very popular. If you make this capsule, these kind of capsules, we are mixing with that concrete, we are mixing with the plasters, and that can be that mixture if you are using for the 3D printing. So your efforts will be reducing, and the thermally we can able to get that more comfortability. So nowadays, actually, Tata actually taking one project. So they're constructing first 3D building in India. They are constructing one post office. How they are constructing,
This is India's first post office to be constructed using the 3D printing technology. It is located at the Cambridge layout in Bengaluru. The building, spread across 1,100 square feet, is made with the help of a 3D printer which pours small heaps of cement. The cement, sand, and a waterproof chemical are added into a churner with measured amounts of water. The mixture then comes out in blocks, which are laid on top of each other, along with iron pillars in between for support. The project is being implemented by Larsen & Toubro at a cost of rupees 23 lakh. With the help of this 3D printing technology, a building can be constructed in any shape.
The whole project to be done in 45 days time. So this is the first time that we are actually using this in Bangalore for actually a public building. The people concerned, the post office, have been asking us to do this building for the last 1 year. So ultimately we concluded the contract, and that's why we are here. Today we are on the 20th day, and so another 3 days by the Friday I think we'll complete the 3D concreting portion of the 3D. The walls will complete. Then we'll put the precast, the roof, and all other things. So in this, everything is done is 3D printed in this building particularly. The idea here is that we have everything is computerized. The whole drawing is given to the computer. You do it in 3D printing. You can do any kind of shape. I think that's the advantage in 3D. I'm not bothered. It's actually the architect's delight. You want to do any building, any shape you want. So we'll do that.
Likewise, we can able to print the concrete material. So whenever we want to incorporate the passage material, that mixer also we can put into the concrete and we can able to print the material. So once it is done, so not only give the structural stability, it is also give that thermal stability also. Like it can able to effectively able to regulate the temperature. So that can be possible. And what is the advantage of 3D printing technology in the building? So you see, whenever you want to go with the conventional building construction technologies, you have materials, you have to select the material, you have to make that concrete mixing, and we have to make the blocks. We have to we need to choose the skilled laborers, and we have to use the tools, and finally you have to build the material. But whenever we want to construct the 3D printing material, so material we can make it, and we have a 3D printer itself. Actually, it will mix all these things, and we can avoid that tools, and we can avoid the blocks, and we can avoid the skilled labor. So it can able to automatically it can able to print that entire structure. So that can be possible. So your efforts will be minimized if you use the 3D technology, 3D printing technology into that commercial buildings. So what are the parameters which will be involved for this 3D printing building material? So it should be extrudable. So from the nozzle itself, so what is the nozzle? If you're using in this nozzle, the concrete mixture has to be easily flow. So if it is struck, it means so you cannot able to print it. And if it is easily flow means, so that is also not acceptable thing. So that proper mixture has to be flow. It has to be extrude. It has to extrude through the nozzle, and it should be having the open time. Like whenever you want to print, you want to pass that material for construction. It should be easily getting solidified. So it has to getting plasticity easily. So then only that time we can have an open time. So that open time must be as less as possible. If it takes a lot of time, means you have to wait until unless it is getting that plasticity. So we need to we need to reduce this open time. That mixture should be having the less open time, and it should be easily buildable, and it should be having the good shape retention factor. So shape retention factor is nothing but, suppose you want to print that material, the printed material having the circular cross section. So after it is flowing in the layer, yeah, so that circular will be slowly flowable. It will be converted into oval structure. So here the shape will be varied. See, here the shape will be varied. So whenever you want to print the material, that cross section might be having the same has to maintain. That is actually what we call shape retention factor. It should be maintain this shape retention factor. And coming to the contraction control, it has to be as quickly as it is converted into solid, and proper doses also we need to maintain for getting this printable material. So these are the applicability of phase change material in various application, and how wherever 3D printing is there, and we can able to print this kind of material. So any phase change material, it is printable once it is converted into shape stabilized phase change material. So what actually the shape stabilized phase change material? It should be leak resistant. So once it is converting from solid to liquid state, it cannot release the heat. Sorry, it cannot convert it into liquid. It should be stuck in the pores, or it will be stuck in the shell. if you make this kind of shape stabilized material, these materials easily printable using the any of the 3D printing technology. So as of now, the any material you can able to print, but we have some limitations like passage material. So that limitations also we can easily avoid this by using this adopting this shape stabilization technologies. So all everywhere any application we can use these passage materials. Okay. So I'll take small break. After that, we can use how to prepare this passage material. What are the various characterization techniques are there, and how we can deploy models for predicting these passage materials. We'll continue in the session. We'll take a 10 minutes break. After that, we will start the session.
Yes, sir. Thank you, sir. Now we have short break, 15 minutes.
ये देख रहे हो
Sir, Ravi Kumar, sir, you can start your session now.
So, as of now, we discussed about it, what are the various types of passage materials and what are the difficulties on passage material. The main difficulties, lower thermal conductivity and leakage problem when you are using in real-time application. So those difficulties we can be addressed by making as a safe stabilizer passage material. So that can be possible if you want to do that encapsulation, like we can cover with that any kind of shell materials, or else we can mix forest like those kind of safe stabilizer material that can be used for real-time application, and it can enhance the thermal conductivity. Meanwhile, it can leakage will be arrested. And after making safe stable passage material, we can incorporate this printing application. Like we can able to we can use in the solar steels for improve the productivity, and we can use in the refrigeration systems also. We can use it, and smart fabrics also we can use. We can incorporate that PCM materials into that smart fabrics, and we can able to print that fabrics, and we can incorporate this the PCM 3D printer PCMs are incorporated into the helmets also, and we can use in the building application once we make this and capsules for facing material, so that we can mix into the concrete and we can able to print that concrete buildings. And finally we can come with that what are the preparation strategies are available, and how to do this facade safe stabilized facade materials, and what are the various characterization techniques are available to evaluate that performance of this system, these materials, and how to deploy these machine learning models. So yesterday we already having this session using those models, with the help of those models, how to predict this performance of the system. The performance not only is the system, and as well as the properties of the materials also. With the help of the machine learning algorithm, we can able to predict it. So first thing is that we can able to encapsulate the phase material. So we have some strategies like nano encapsulation encapsulated phase materials is possible. So up to nano levels we can synthesize. Up to nano levels we can able to make that capsules that can be possible. So here I'm taking one phase material. So that material was salt, that is sodium nitrate and potassium nitrate. So this is mixture of 60%, 40%. This is actually most usually we can call it as a solar salt. So this is actually melting point temperature in the range of 220 degrees centigrade. So that for this is for medium temperature application we can use it. So first we can make this salt, we can mix into the water, and once completely make this solution, so we can make that eutectic PCM material. And eutectic, there's a combination of any two materials. So that here I'm using two salt material, inorganic eutectic mixture I'm developing. I was developed. So after that, we are removing the water by heating around 120 degrees centigrade for 2 hours period of time. So if you above 120 degrees centigrade, so what are the water molecules will be that is evaporated? Only salt will be left over. So after making this salt will be again you are mixing with the water, and we can stir for 800 RPM for 10 minutes in the magnetic stirrer. And after that, we are mixing some binding structures, PAN 80s. This is the chemical we used to use for facet material to hold that cell material. So after that, we are using a TEOA solution. So the tetraethyl orthosilicate, this is actually giving that silicon oxide cell material. So for making the cell material, we have to mix this chemical composition. After that, we are adding it to the ammonium hydroxide to remove the bonds of tetraethyl groups. Only if you add this ammonium hydroxide, these bonds will be break. Only silica will be coated over the phase change material. So completely your PCM was capsuled with the silicon material. So same also say the procedure can added up. Instead of TEOA solution, we are using TNBT solution. That tetrabutyl titanium we are using. So if you do that stirring process, automatically these bonds will be break. Only titanium oxide will be coated over the phase change material. So it is actually nano level synthesized. I want to make sure I have to confirm that whether it is perfectly capsuled or not. So in the nano level you want to see means I have to go with that same analysis. So you know very well scanning electron microscopy. So this is the pure PCM, and remaining these are the silicon oxide coated phase change material. So this is actually capsule like structure, and titanium oxide cell encapsulated phase change material. This is also capsule like structure, and I want to check that dimensionality. So there is a particle distribution analyzer, one equipment will be there. If you give the samples, so they can check that what is the dimensions of the each and every capsule. So most of that capsules will be in the nano range only. It is very confirmed that. So our prepared phase change material nano level encapsulated. So after that, there is a two test we have to perform, that is chemical stability. We need to check it. So once you prepare the phase change material, so whether the cell material is making any reaction to the phase change material or not. So what are the phase change material you are preparing? That phase change material, it should be not react with that outside cell part. If it is the shell should be physically available, and it is not making reaction to that, it is not having any chemical reaction with the PCM material. So that you have to ensure. So this is that can be checked with the help of X-ray diffraction spectroscopy, and FTIR also, Fourier transformation infrared spectroscopy. This is for checking the peaks. So most of the peaks will be available. The base PCM peaks will be available here, and encapsulated PCM also same available. Silicon peaks also visible, and titanium peaks also visible. All chemical compositions will be available except all chemical compositions will be available. So it is confirmed that it is chemically stable. Even we can check that functional groups. So functional groups is nothing but like any bonds will be there, like OH bonds, or like CH bonds, CC bonds. So these are some kind of bonds will be there. Whether these kind of bonds will be disturbed or not, we can able to check with the help of FTIR spectroscopy. So mostly all groups are available here. So there is no variation. So this silicon oxide group will be available. This is the pure PCM peaks will be there. Same peaks will be available here also. Apart from that, extra new peak will be appearing, that is silicon oxide. So silicon oxide is perfectly coated here, and here titanium oxide perfectly coated here. So from the XRD plots and the FTR plots, it is confirmed that there is no chemically disturbed after doing that encapsulation. So the most important thing is that I want to check that latent heat value. So latent heat value is very important. So based on the latent heat value, so I can able to check that whether this material will be feasible for storing the energy or not. So here, after conducting that DSC, differential scanning calorimetry analysis with the different heating rates. So what I can do with the help of this equipment, I can able to measure the melting point temperature, and I can able to measure the latent heat values. This is the latent heat value. So before that, my PCM was having the melting point temperature, latent heat value. It is around 116 kilojoule per kg. So for 1 kg, it can able to store 116 kilojoules of heat. So that much heat will be stored. If you do that encapsulation, so you can see that the latent heat value will be reducing. So this is quite common. The shell particles will be completely covered, so that latent heat value will be reducing. So that will be common phenomena will be happening. And coming to that, another thing, phase melting point temperature. So during that charging condition, during the discharging condition. So the melting point temperature, that difference we call degree of supercooling. So the degree of supercooling is slightly deviated. It is much not. It is not that much deviated. So during the heating, it is having the 228 degrees centigrade. During the cooling, it is releasing that at 220 degrees centigrade. So here the only significant temperature difference only observed, and it is quite improved. Very small improvement was observed in that silicon coated salt material, and if it is titanium oxide, it is very less amount will be, we can see. So this is actually a kinetic model. So I just want to find out that activation energy values here. So these activation energy values I want to find out means, so what is the significance of activation energy? Suppose whenever phase transition was observed, so whenever having reaction, so to initiate this reaction, we need some energy. So we need some small energies requirement. That energy we call it as a activation energy. So not only for the phase application, suppose your any chemical reaction is happening. So for initiation of the chemical reaction, we need to supply some energy. So that energy we call it as a activation energy. So that energy we are also calculated for base material. It is having very high activation energy value. After coated with this material, so it is slightly reducing. It is reducing that activation energy values. And specific heat capacity. So this is also very important property. So if you want to whenever you are supplying the heat cannot not only stored in the latent heat form. So from suppose if you take the salt material, so our material having the 220 degrees centigrade is the melting point temperature. Up to reaching 220 degrees centigrade, so the material having, it has to store some heat. Okay, so that at that state, the PCM was not changing its phase. It is still in the solid state only. So that is actually sensible heat. So that sensible heat is mainly depends on specific heat capacity value that already earlier uh, we already discussed. So if the CP value is more, my sensible heat storage capacity also improved. So if you CP value is more, so more sensible heat value. If the latent heat is value is more, so more latent heat value. So obviously altogether we can have a more energy storage capability will be there. So apart from that, we are conducting the thermal, we are checking the thermal conductivity. So here the thermal conductivity's value was improved. So my pure PCM thermal conductivity value was 0.452. Once you coated with silicon oxide, so it is slightly improved. And if you coat with the titanium oxide, it is slightly improved. Why? Because here I was making the cell with made of silicon oxide, and titanium oxide. So these silicon and titanium are the organic materials. So which is having the high thermal conductivity as compared to that salt material. So that's why this thermal conductivity is slightly improved. And coming to that, my stability, thermal stability, I want to check it. So thermal stability, this is also very important phenomena. So whenever you are heating the phase change material, it is up to certain temperature. It is once it reaches the melting point temperature, my PCM was solid state. Once it is crossing that melting point temperature, it was in the liquid state only. So if keep on heating that, if you keep on keeping heating the material at certain temperature, what will happen? Your chemical structure will be destroyed. So it will completely convert into vapor. So that vapor cannot be retrieved back. So if you take the water and all, so it will be solid state in the ice form. If you heat that, it will be converted to the liquid. After that liquid, it will be converted into vapor. But real chemicals, actually, what will happen? Suppose if you take the paraffin wax, so you are heating the material, so the material will be converted into liquid. If you're still heating, so that liquid paraffin wax will be converted into vapor. If you condense that vapor, it cannot come back to the its original chemical structure. So it will be chemically completely destroyed. So at what temperature your material was degraded? So that you can check it. Using the TGA analysis. So if you conduct the TGA analysis, so my degradation temperature was initiated at 600. So your chemical will be safe enough at this temperature itself. Up to 600 degrees temperature, you can operate this material. So you can give the temperature up to 600 degrees. Once it is crossed 600 degrees temperature, so obviously your material will destroyed. But if you coat with that silicon oxide and titanium oxide, so your degradation temperature was little bit higher. So it will be little bit extended. So 650 degrees temperature, so it will be degrade itself. So this 50 degrees temperature significant improvement will be happening. So my operating temperature was improved. So that is the significance of conducting the TGA analysis for the material. So after that, I want to conduct that leakage test. So if you check that material at room temperature, so my PCM was in the solid state, and if you coat it with the silicon oxide, all are in the solid state. If you give that above melting point temperature, so my melting point temperature in the range of 225 degrees or 228 degrees centigrade. If you give the 260 degrees, it is crossing the melting point temperature. My PCM was converted into liquid. It is converted into liquid. But if you encapsulate it with the PCM material, so the material was converted into liquid, but it is stuck in the cell material. So it is not leaked out. So if you see that even after 260 degrees temperature also, my PCM was not leaked off, not leaked. So it is perfectly safe stabilized. So that we can confirm it. So after that, we are developing that NN models to predict that DSC data. This is already we discussed in the earlier classes, but I'll explain it for hands-on session. I will explain how to conduct this modeling. So here what I'm doing is, so here the type of PCM. So here how many PCMs are available? So we have a 3 PCMs. So one is the solar salt PCM. Another one is that silicon oxide PCM. Another PCM is a titanium oxide shell based PCM. So 3 types of PCM was there. That is actually I'm passing as a one input. And here DSC I have performed with different heating rates. So here, if you see that any material I'm performing with different heating rates. So 5 degrees per minute, 10 degrees per minute, 15 degrees per minute. So 3 heating rates are passing. That is the one of the input we are passing. And temperature range from the 200 to 260 degrees temperature range. That temperature range also one of the input we are passing into the neural network, and we are able to predict that heat flow. So what is the heat flow? So here the DSC we are getting the heat flow, that heat flow curve, heat flow value. So this is the output I want to predict. So that actually we are predicting. We are conducting the. I already spoke about this sensitivity analysis. So here's a lot of sensitivity parameters which will be involved. So here, number of hidden layers we have to change, and activation functions also we need to change. And here also activation function we need to change. and a lot of things we need to change. So after conducting several sensitivity analyses, and finally at this network, so if you put the 36 hidden neurons, so my and the activation function, if you provide tan sigmoid function, so I'm getting that highest R square value. So RMSE or R square value is the statistical parameter. So we already discussed. So higher R square value, lower RMSE value, which network having which network having these values. So obviously that model we can say, we can conclude it as a best neural network model. So among that, this network we can use for prediction of the DSC data. So I'm passing that unknown parameters, like unknown parameter. So same the second kind of material. So silicon oxide, I was conducted with different heating rate. What heating rate I'm performing is here in between 10 to 15 7.5 degree centigrade data was passing. So it is predicting some value. So I was comparing with that experimental data. So very significant, very less value it is predicting. So if you do these kind of models for prediction of properties, DSC data, so error value, the melting point temperature. This is the melting point temperature. So the melting point temperature is exactly predicting, that is error deviation is 0.01%, and latent heat value. So under this curve, what is the area will be there? That will be signifies that latent heat value. So my latent heat value also exactly predicting. So that is the model we are developing. So this is the very huge data we having. So that's why we are using NN model. So even more data will be so even more data was there, so that we can able to perform with the machine learning models also. So another preparation strategy was, so including that porous structured material. So incorporating the porous structure material. So in this porous structure material, so some kind of multi-wall carbon nanotubes also, similar kind of porous structure material was there. So what I'm doing here, I'm taking another salt, lithium nitrate and sodium chloride. So I was preparing some binary eutectic mixture using the magnetic stirrer. After that, I just included that nanoparticle. So I just impregnated this nanoparticle here over here, and after that we are heated up, and after that doing the ultrasonication, after that doing the mixing process. If you do that repeatedly, and finally it is multi-wall carbon nanotubes are well mixed with the phase change material, and after that once the phase change materials are ready, so that it is completely well mixed with the nano enhanced phase change material. So the nanoparticle size and all, I want to check it. So what I can do, I can put that nanoparticles, I can put that these nano enhanced phase change material into SIM, and I can check that what is the structure over here. So here the structure and all, usually these nanoparticles or multi-wall carbon nanotubes are very long in structure, very long in structure. So that I can check, I can see over here in the phase change materials. So after that, we need to conduct that uh, how it will be sedimented. So mostly these nanoparticles will be segregated at a liquid state. So whether these nanoparticles are well mixed or it is sedimented, that we want to check it. So after at the liquid state, the all PCM materials, all composition. So here I mixed with the three composition. So one is that 0.25% and 0.5% and 1% mixes I was developed. So these materials, these materials I mixed over here, and after 10 days period of time, sorry, 3 days period of time, I was keep on I was keep on maintaining in that liquid state only. So above melting point temperature, even after 3 days also, the nanoparticles are not sedimented over here. It is still well mixed to the phase change materials. So similarly, I have to check the chemical stability. That can be possible by using that XRD plots and FDR plots. If you see multi-wall carbon nanotubes, that is nothing but only carbon structure will be there. So that my carbon peak you can see. And this is the lithium nitrate and the sodium chloride peaks are available. So this is the pure PCM. The pure PCM, all sodium chloride and lithium nitrate peaks are available. If you well mix these two, multi-wall carbon nanotube to the phasage material. So it should be having the all peaks apart along with this multi-wall carbon nanotube also. So this peak will be visible here. So this peak also we can see over here. So this is the peak we are seeing. So apart from that, there is no other peaks are visible. So we can confirm that there is no chemical reaction was occur. There is no phase. There is no few phases are formed. And meanwhile, FTR analysis, we can see whether functional groups are any disturbed or not. We can check. These are the functional groups of the pure PCM. So after adding this multiple carbon nanotube, so same functional groups are maintaining here. So it is confirmed that they are completely chemically stable. So PCM materials are after mixing this multiple carbon nanotube, it is not changed its properties. So this is the DSC plots, differential scanning calorimetry for checking the melting point temperature. So this maximum, where actually we are getting the maximum P, the corresponding temperature we can call it as a melting point temperature. The area under over this curve that we can call it as a latent heat value. So if you heat this with the different heating rates like 2.5 degrees centigrade per minute, 5 degrees centigrade per minute, 7.5 degrees centigrade per minute, my melting point temperature will be significantly improved. So that can be seen in the all PCM samples. This is the pure PCM sample. This is the 0.5 and 0.25 and 0.5 and 1% multi-wall carbon and tube mixers. So these are the latent heat values. If you see pure PCM having the 292.5 kilojoule per kg. So that means 1 kg it can able to store 292.5 kilojoules. So this value was reduced if you mixing the multi-wall carbon nanotube mixtures. So similarly in the latent here activation energy values also will perform here. So activation energy value with the help of various kinetic models. So activation energy values also it is quietly improved. Significantly it is improved, and with the addition of various fractions of nanoparticles. And coming to the thermal conductivity, so that is why we are mixing this multi-wall carbon nanotubes. So main agenda is to increase the thermal conductivity. So that's what we need to check. So here I was conducting the thermal conductivity test. So here pure PCM thermal conductivity was around 1.62 watt per meter Kelvin. If you mix different fractions, so suppose if you're mixing 0.25, it is increasing, and 1.5 multiple carbon increasing, and 1% if you are adding, it is also increasing. So after finally 1% multiple carbon nanotubes we are adding, so 38.59% significant improvement was observed over here. And this is a one kind of test actually. So where you are adding that nanoparticles, so how quickly it is charging, how quickly it is discharging. So what is the use of adding this nanoparticles? So to improve the thermal conductivity. Suppose if we increase the thermal conductivity, how it will affect? So why we need to increase the thermal conductivity? So if you increase the thermal conductivity of the material, so it will quickly charged. So because of the more thermal conductivity, if you put the heat, if you give the heat, it is quickly charged. It will easily absorb the heat. Otherwise, if it is thermal conductivity is very less, if the thermal conductivity is very less, it will be act like insulator, so that the heat, whatever the heat you are giving, it is not absorbing the phasage material. So that's why we need to increase the thermal conductivity. So if you conduct this experiment, so what I'm doing here, I'm putting that various PCM material, I'm heated up. So here the charging time it is significantly reduced. So that is what actually. So from here the time versus temperature graphs, you can signify that. So we adding this multi-wall carbon nanotube. So this is the pure PCM. It takes a lot of time. Suppose for 20 minutes it reached around around 220 degrees centigrade. But same composition, same 20 minutes time. If you take this multi-wall 1% multi-wall carbon nanotubes, so it is significantly temperature was rise as compared to the pure PCM. So that's what actually we see. And similarly, in the discharging also, while releasing the heat, so here, suppose at 225 degrees, if you want to get the 225 degrees Celsius, so it takes 10 degrees, 10 minutes period of time. But if you go with that 1% volume fraction, so it takes, pure PCM, it is to discharge time, it is also decreasing. So that is what actually we can see here. So percentage reduction of charging discharging time, it is reducing. So, and here TCA experimentation, yeah, I already told that if you conduct the TCA, so we can see the onset degradation temperature points. So this is my onset degradation temperature point here. So my nano enhancer PCA material, it can having the temperature up to 650 degrees temperature. So I can effectively operate this material up to 650 degrees temperature. But my PCM melting point temperature at 230 degrees centigrade only, but I can effectively operate this material up to 650 degrees centigrade. That can be possible. And one more thing, stability analysis, we have to cycling test or thermal stability or thermal durability study we can perform. So that means I already told PCM, it is keep on heating, keep on cooling. So repeatedly you are doing different thermal cycles. So my PCM properties will be changed. So it is your latent heat value, your thermal conductivity value will be affected. So how affected it is, we can check it. So here I performed it 500 thermal cycles. So I just keep on heating and cooling above the melting point temperature. I just heated up above the melting point temperature. After that, I cooled below the melting point temperature. So keep on doing for 500 thermal cycles. So my latent heat value will be reducing slightly. It's not drastically, it is reducing, slightly reducing. So for pure PCM and 1% multiple carbon nanotubes also, it is slightly reducing. And my chemical structure also, it is not varied even after 500 thermal cycle. Even thermal conductivity is also is not reducing. So that we can check it over here. And here also I was developed ANN modeling. So here how many samples are there? 4 samples are there, volume fraction. So pure PCM is there. So here pure PCM is there. 0.25 multiple carbon and mixture is there, 0.5 and 1% multiple. 4 samples are there. So 4 samples I was passing as a one input parameter. And heating rate. So here DSC was performed with the different heating rates. So here how many heating rates? 3 heating rates are there, and that is 2.5 and 5 degrees per minute and 7.5 degrees per minute. And the temperature range I'm taking as a 200 to 270 degrees centigrade. So that input parameter, finally heat flow, I was able to predict it. And here also I was conducting that sensitivity analysis. For the sensitivity analysis, I was calculating that RMS and R square value for different networks. So different network topologies. And finally at neuron numbers, hidden neuron number 122, I'm getting that lowest RMS value, highest R square value. So at that model, we are passing the unknown parameter, unknown experimental data. So that was compared with that predicted value. So there is a slight deviation of the melting point temperature, and there is a slight deviation in the latent heat value. So it is effectively predicting. So unknown composition, unknown heating rate, if you are giving, so I cannot conduct the DSC experiment separately. So what I can do, so simply I already have the developed ANN model. Simply that data we can pass it over here. I can get that predicted value. And there is another another encapsulation technique was there, that is adding the expanded graphite. So this is the expanded graphite. So the advantage of using this expanded graphite, this is the porous structure material. This is the expand graphite flakes will be there. So in this graphite place, what actually, this is like a kind of cracker. Diwali actually we used to snake kind of small cracker will be there. So what actually, if you burn it, it will be expanding like that. So similarly here also, some graphite flakes will be there. So these graphite flakes, if you put in the muffle furnace for 800 degrees temperature, so these graphite flakes will be expanded. So this will be having the more cost, more pore structure. So the because of the pore structure, what are the liquid PSN material? If you are mixing or you are mixing with expanded graphite, it was stuck over here. It was stuck in the pore structure. So here also you are doing that magnetic stirring. This was mixed to the liquid phase change material, and after that doing that ultrasonication. So the sonication was used to for disperse properly disperse the material. So after that composition was ready. After that make the pellet. So this is actually safe stabilizer phase change material. So it is completely locked. Your liquid phase change material was completely locked over the this porous structure material. So here also I want to check that the characterizations. I want to check that chemical stability using the XRD and TR plots. So if you XRD plots for expanded graphite, this is also carbon structure. So this carbon structure and this peak, we can see this in this peak, and this is that pure PCM structure, lithium nitrate and sodium chloride. So these have the peaks. If you mix different composition, 3%, 6%, 9% mixture, so these same peaks will be visible. See, expanded graphite peaks also visible here. Expanded graphite peaks also visible here. But apart from that, there is no other new peaks are visible. If new peak is you can see means, so there is some chemical reaction happen between the expanded graphite and pure PCM. But there is no new peaks are available apart from these peaks. So what you can confirm? So it is uh, chemically stable. That means expanded graphite was physically appear, but it is not creating any reaction to the phase change material. So similarly, functional groups also we can check it. This is the functional groups of the pure PCM, and this is the functional groups of the expanded graphite. This is the only pure carbon, so that's why it doesn't have any functional groups. If you mix this phase change material to the expanded graphite, your functional groups of the PCM was not disturbed. It is still remains same. So from these plots, we can confirm that there is no chemical. There is no okay. These materials are chemically stable. These composites are chemically stable. So I want to check that same analysis. So what actually this is the pure PCM particles in the micro level range. If you see, so these are the PCM particles. Salt particles will be there, and expanded graphite actually the porous structure. This is the porous structure. Honeycomb structure will be there. If you mix the PCM to the expanded graphite, the PCM particles are completely locked over the these graphite flakes. These are the graphite flakes. It is completely locked over here. So what will happen if you heat the material over here? If you heat the material over here, so this liquid PCM will be, it is completely locked in the pores of the material. So it is not leaked out. So that's what we can confirm from the SEM analysis. So this is the BET analysis, how the pores distribution. So I want to check that. I was using that pore structured material. The pores I want to check it. That the pores dimensions I want to check it. So most of my pores are in the range of 5 to 10 nanometers, and below 10 nanometers only I'm getting. So your nano level range, it is locking your passage material. That you can confirm with the BET analysis. And the leakage value, this is the 3% expanded graphite. If you use that, they're having the 15% leakage will be there. If you add with 6% expanded graphite, your leakage value will be reducing. And if you add 9% expanded graphite, 5% only it is leaking up. So you can confirm that 9% expanded graphite with phase change material, it is effectively arresting the leakage problem. And this is that latent heat value, melting point temperature value during the heating and during the cooling. So these are the values. If you're adding this 9% expanded graphite, your latent heat value will be reducing. Earlier actually 292.5 kilojoule per kg. If you add 9% expanded graphite, it will be reduced up to 195.1. So that means 1 kg pure PCM having the latent heat value 292.5 kilojoules of heat can be stored. But if you make with 9% expanded graphite, the PCM can hold up to 195 kilojoule per kg. So there is a reduction in the latent heat value. So this is actually reducing the storage performance, and the meanwhile it will be add on advance to the thermal conductivity. So if you see the thermal conductivity, pure PCM having that 1.7 kilojoule for watt per meter Kelvin. But if you increase that expanded graphite, so my PCM PCM thermal conductivity is significantly improved. So 9% expanded graphite PCM thermal conductivity, it is around 10 watt per meter Kelvin. It is went up to 10 kilowatt per meter Kelvin. So that actually we can see. And these are the different DSC plots at different heating rates, 5 degrees, 10 degrees, 15 degrees per minute we are conducting. And these are the activation energy value using this differential DSC data. So various kinetic models we can deploy and we can get that activation energy value. Adding that expanded graphite, activation energy value will be significantly improved. So I already told that activation energy value is nothing but whenever you want to initiate that reaction, so we need some energy. So that energy is nothing but activation energy. So here adding up to 9% expanded graphite, my activation energy value will be increasing. So this is the thermal stability test. So up to 500 thermal cycles. So it is from zero thermal cycle, I having some properties at 500 after 500 thermal cycle. So my latent heat value, it is fluctuating in nature, but it is obviously in the same range only. It is not deviating. So that's what melting point temperature and latent heat value. This is just like deviation, small deviation was occurred, but it is almost like 5%, 10% deviation only. It will be fluctuating. It is not so. It is confirmed that it is thermally reliable even after 500 thermal cycles also. So this is the charging and discharging curves. So if you take that pure PCM, so this is the pure PCM curve, and if you take 9% expanded graphite, my charging time was significantly reduced. So that means if I 220 degrees 220 degrees temperature you want to get it means, so how much time it will take? So around 250 seconds only, but same 250, 220 degrees centigrade, pure PCM, it will take around 1000 seconds. So there is a drastic reduction was there. So drastic reduction was observed in the charging and during discharging also. So that is the advantage. So if you add that expanded graphite is nothing but carbon. This is having the high thermal conductive material. If you increase the thermal conductivity of the material, so obviously my charging time will be reducing. My discharging time is also reducing. And this is that corrosion stability. So this is the corrosion stability. So what are the material I'm putting? So just keeping into that all the material like aluminum, copper, galvanized iron, mild steel, stainless steel. So these pieces I just dip it into that PCM material. I just dip it into the PCM material. Like so this is the pure PCM. Uh, this is the pure PCM, and this is the 9% expanded graphite material, and this is that below melting point temperature, and this is the above melting point temperature. I just keep on this material for around 24 weeks. I just keep simply putting this material. So I just calculate the corrosion rate and just calculate the depth of corrosion. So using this 9% expanded graphite material, the corrosion rate was reducing. That was actually significantly. So I already told organic matter like salt kind of material, you want to store in the any of that metals, those metals will be corroded. So as compared to that, among all, copper having the more corrosion even in the pure PCM and 9% composition also. But if you go with that stainless steel, if you go with the stainless steel, it is a corrosion rate was very less. So what are the material we are preparing? So if you store into the stainless steel based container, so my corrosion will be very less. But if you store in the copper, my corrosion will be very high. And same ways, aluminum also having the more corrosion as compared to the stainless steel. So here also I was developing that modeling, neural network modeling. So here expanded graphite and heating rate, and here the conversion rate. Instead of that, earlier actually we have a huge data. So temperature data I'm considering, but here I'm taking conversion rate. So here the conversion rate is nothing but, suppose here how much value. So suppose in this area, in this DSC plot, so this portion only I'm taking. So this is from enter this enter the sorry, wait, from this area divided by entire area if we take, so that is actually the conversion rate we can say. So this conversion rate, if it is varying, so my temperature also will be varying and my heat flow is also will be varying. So these two data I was taking, this data will be used to predict with the help of the model and modeling. So here what I'm doing, expanded graphite. So here three compositions I'm taking: pure PCM, 3% expanded graphite, and 6% and 9% expanded graphite I'm taking. And heating rate actually, we are conducting the DSC data with different heating rates. So what actually having 5 degrees per minute, 10 degrees per minute, and 15 degrees per minute. So these heating rate we are passing. And finally, a model was developed. Here also we are conducting the sensitivity analysis. Finally, we are getting the best value. So similarly, and TCA data also we can able to predict it. So TCA data also, sorry. So TCA data also here I was implemented particle swarm optimization. Yesterday already spoke discussed about this hybrid algorithm, AN and PSO algorithm. So here the type of PCM and heating rate and the temperature data, and finally how much mass loss will be there. The TCA data also we can able to predict it. So we are conducting the sensitivity analysis. So particle swarm optimization already told. So there is some sensitivity parameters will be there, number of hidden neurons and the cognitive coefficient and C1 value and social coefficient C2 value and population size. So after conducting all these things, so finally we are getting the best model. At this best model, we can able to predict the TCA data. So similarly, this TCA data also we are conducting ANFIS model. So percentage of expanded graphite, heating the temperature. We already spoke about this in ANFIS model. So here also mass loss is predicting. So we are conducting that we are conducting the sensitivity analysis. Finally, among all GBEL membership function, it is showing that best performance. So as of now, these models actually with this TJ data or whatever maybe DSC data, I was developed only NN models and hybrid model. But how we can develop this machine learning model? So that we can do in this hands-on session. So, um, so I have a data. I'll show you that what is the data I'm having. So this is my actual data. So here actually, so this is my input data. So in this input data, um, uh, this is the type of PCM I'm taking. So actually this type of PCM, it is actually text data. So what I'm doing, I was converting into numeric data. So it is a loading with there is no expanded graphic. That composition I'm taking that is 0. Okay. If the 9% expanded graphite I'm taking, that is I can take it as a 1. I can take it as a 1 here. And heating rate was also I was normalizing. So normalizing techniques also I already discussed earlier. So this is the 0 uh, and this is the conversion and this is the temperature. So finally I want to predict that a mass loss. This is the data I want to predict. After doing the normalization, we have to do the randomization. So for shuffle the data, we need to shuffle it completely. Okay. So this is the final data. After pre-processing is all the data. So I'm taking that my finalized data. So this is the finalized data. So this is the type of PCM, and this is the heating rate, normalized and randomized data. This is the temperature data, and this is the mass loss data. Okay. So now we have to model machine learning using Python. So we know that this is the Colab for a Python compiler platform. So first thing is that we need to import the libraries and we need to import the data. So in this first we need to upload the data where actually I'm storing. So this is the data I'm having. I'm storing the data ML and I was opening. Sorry. Data ML. So now data was load here. So now the data was load here. So these are the libraries we need to import. So pandas, NumPy, and pandas and NumPy actually for model development, and matplotlib.pyplot. This is for graphical representation, and Seaborn also, like this is the one library for graphical representation. So first we need to import this library. So we already imported, already wrote the code, and we just run it. So now it is enable one tick mark green color. So now the code was run successfully. And after that, we need to read the data. So after that, what we need to do? We need to read the data. So here for the reading, so my data was stored in the Excel file. So my data was stored in the Excel file. So in the Excel, and sheet name was she1. So this copy we need to give the here. So this path we need to give over here. So here what I can do, I can copy path. So here, if you click that here, we can get that copy path, and here we can have to paste it. We have to paste it. So that copy we need to paste. After that, run over here, we'll get it. So my data was loaded. So my data was loaded. What is my columns? Type of PCM, heating rate, temperature, and mass loss. Okay. After that, so we can go to the next block. So here I can see that first head values. So head of 2 is nothing but first 2 rows data I can see, and the tile data means last 2 data. So I can see. So these values we can check it. So if you use this code tile, so how many rows number will be there I can see here. And here data dot save will be there. So this block if you run, I can see how many columns are there, how many rows are there. So for totally 400 rows are there and 4 columns are there. And if you run this block data.columns, you run this block data.columns, I can see all the columns. So what are the columns over here? Type of PCM, heating rate, and temperature and mass loss. Okay. After that, there is a another block will be there. That is information, data information I want to check. So this is the data information, this block. So for checking that data information, what kind of data it is. So type of PSM actually 0 to 1, that's why it is showing the integer data. And if it is any decimal value, it is showing that float value. Like that, if you more number of data, so that the more number of digits will be there, it will show the double. Like that, it type of data it will show here, data information. And data describe. So this block, if you run, you can check that how many counts will be there, how much 20% data where it is lies, and 50% data where it is lies, and 75% data where it is lies. We can check it over here. And there is another block. So I already told, so for data preparation and all, you want to check that missing data value. So if any missing data value, we need to fill it. Otherwise, more missing data value and all, so that is not useful for modeling the data. So that you can check it here. If you run this block, you can check. So type of PCM column, there is no missing value, and heating rate column, there is no missing value. Temperature and mass flow, there is no missing columns. So we can model this data effectively. And this is the pair plot graph will be there. So there is a pair plot graph will be there. So this pair plot, you see, using this pair plot graph, you can check that relation among the data. So you see, so what are the parameters I was considered here? So type of PCM, heating rate and temperature and corresponding mass loss, right? And corresponding mass loss I was taking. So type of PCM versus mass loss, it is 0 and 9% expanded graphite only. And how many heating rates are there? 4 heating rates are there here. So 0, 0. This is actually normalized data. It's not like pure denormalized data. It is normalized data only. So we can see that relation. We can see the relation over here using this pair plot graph. So after getting this pair plot graph, we can run this heat map graph. This is the heat map graph. So it can see that relation, linearity relation among the parameters. Suppose let us take, so if you see type of PCM versus mass loss, there is a value of minus 0.35. That means, so 35% linearity was there. So more linear, first linearity will be goes to temperature only. Temperature data, more linearity will be there. And heating rate having this second linearity, this is inverse linearity will be there. Okay, so that means, so if you adding that, if you take that by type of PCM, suppose if you change that nest parameter, like if you change that nest parameter, like expanded graphite particles you are adding, so mass loss will be reducing. So that you can see. So you can check that linearity deviation among that combined parameters. So here heating rate, so very less linearity will be there, and temperature having the more linearity. So positive linearity, that means adding the temperature, mass loss will be having more. Okay. So there is a one more block will be there. That is a distribution plot. If you run this plot, so most of my data was lies in the range of this range only. So my mass loss was will be range in the, it will be in the range of 4% for 40 to 1%. This is the actual normalized data. That means 100 to 40% data only will be falling in this range. And if you want to check that scatter plot, temperatures versus mass loss, how it will be varying. So we can check it over here. How the relationality will be there, we can check it over here. And we can check the data types. What are the data types? Type of PCM actually integer, and the remaining columns are actually float. So now coming to that, now we have to assign the input parameters and output parameters. That is very important. So my output value, Y value will be mass loss. So mass loss has to be stored in that Y term only, and the remaining values are considered as the X value. So what are the machine learning model will be there that has to be have the relation between the Y and X only. So Y is my output parameter and X is my input parameter. So here my column, entire columns, the last column mass loss will be considered as a Y term, and among all the data, if you drop that mass loss, except mass loss, remaining data will be there. That data will be having stored as a input parameters. So this is the X is stored as a drop of mass loss. That means if you remove the mass loss, remaining data was the input parameters. And if you having the only mass loss, that is the output parameter. This is the assigning the training and, sorry, this is the assigning the input parameters and output parameters. So this we need to run it. So now it will taken as y is the mass loss and remaining parameters is taken as a input parameter that is stored in the x. And rest block is actually remaining block actually we need to split the data. So once the we already done the data preparation, we are doing the normalization, we are randomization we are done, and we are assigning the training and testing. Now we need to split the data. So that means here if you check it over here that there is some fraction was there, that is 0.2. Test size was 0.2. That means so my testing data size was 20% only. Okay, suppose if you want to change that parameter, so splitting ratio you want to change. So 70:30 if you want to change, if you give means, so 30% is the testing parameter. So 0.3 we can give. So here the test size is 0.2. That means 20% data was going for the testing and the 80% data was going for the training. So this splitting we need to do. Now, as of now, we are doing the data preparation. We are assigning the data and we are splitting the data. Now we need to develop the models. So for developing the model, first we can check it linear regression model. First, we need to import the linear regression model. So this importing this linear regression model, it will be available in sklearn.linear model. Okay, in this library, the linear regression model will be available. So in this linear regression, I was stored in as a LR. So now we need to fit the data of training, Y data and X train data. So here splitting the data was done in the training testing and training testing. Okay, X parameters and Y parameters are split into 20%. So now trained data input value, trained input value, trained output value was fitted. So here now data was fit, and now we need to predict the test data. So here after developing the model, so using the training, we need to test the data. So we are passing the test value, and after that we are predicting the values, X trained data. So after that, so we are comparing the trained value and tested value. So if you run this one, if you run this block, we are adding the linear regression model. So linear regression was developed and the testing data also predicted. The testing data was predicted. So this is the values actually, the tested actual value and the tested predicted value. Okay, so there is a very huge differentiation was there. Actual data was actually 0.59, but a linear regression model was predicted to 0.51, right? And if it is second data, if we see 0.94, but it is or predicted 0.97. So this is not good. So what I can do, we can move with the next model. We can move with the next model, and we have a model like polynomial regression. So for importing the polynomial regression, first we need to import the polynomial features from the sklearn dot preprocessing. And here also polynomial regression also, this is a kind of linear regression. So that's why this is also we are importing. Now here the degree polynomial regression have a one more sensitive parameter, that is degree. Ninth order polynomial regression was developing. Suppose you want to develop five you want to develop, so you can put degree is a 5. You can put it like that. So now you can run, you can get the data. So model was developed and it was predicted. If you see actual versus predicted, here also some huge deviation was there. So here is actually 0.59 is actual value, but it is predicting 0.59. So this is also not good. So we can move to the further one. So likewise, decision tree. So decision tree also, we have to import from the sklearn.tree. From this library, we have to import the decision tree regression model, and we have to fit the data, and we have to develop the model. Once developed, it is actually predicting the data. Likewise, each and every model, predefined model, we already developed. And this is for random forest regressor model. So if you run this block, we'll get that actual versus predicted data. And we already told her previously the Gaussian process regressor. If you run this one and here also fit the data, and after that it is predicting actual versus predicted. And here, how well Gaussian process regressor it is predicting. I already told sometimes the Gaussian process regressor effectively predicting for complex data. So it is 0.98 only. So some points are somewhat deviated. You can cross check it. So how well it is predicting with the help of this plot. And we have another model that is support vector regressor. This is also one kind of machine learning model. Actually, yesterday I haven't discussed about support vector regressor. So this is also one kind of machine learning algorithm. So it is available for classification data and the regressor data also. This is also somehow predicted. And now KNN model. The KNN model actually, first we need to check that K value, at what K value it is giving the best RMS value. So we need to check the sensitivity parameter. So first we have to run this code. So in this block, what are the code will be there? We need to run it. We are importing the neighbors block from the scalar. After running this one, we have to check that RMS value at the particular K value. So where actually the least RMS value we are checking. So here you see my RMS value was lower at this range only 0 to 5 value. So but actually at what K value we don't know. So that we can check in the data. So in this range actually which is the lowest value at K value. So 0 to 5 range only, but K value at 2, I'm getting the least RMS value. So I can fix K value is equal to 2. So I can move with the next code and the KNN model. Now I can pass the neighbor value, K value 2. So it's already there 2. So now run the KNN regressor. Now it is predicting. So that is actually earlier code will be useful for find out the K value, best K value. After find out the best K value, we need to give the K value over here and we have to run it. So this is also predicting for some data. And similarly, we have another models, like a lot of models are there. So machine learning is not like stick with just only few models. We have a lots of models are there, and we have a quantum regressor models also there that actually we can check it in that YouTube. And this is also something it is predicting. And ridge regressor models is these are the actually regressor kind of models. So linear regression kind of models. Ridge regression model is also something it is predicting. And loss of regression model. So this is also a kind of machine learning model. This is also something it is predicting. And Bayesian ridge model. So I already developed this kind of course. So it is very simple. So no need to worry about that coding knowledge and all. So if you have an experimental data, so simply we can load it, and after that simply run this block. That's all. You will get that entire values. And elastic net. This elastic net regression model. This is also one kind of machine learning model. This is also running. So this is also predicting some value. And gradient boosting regressor model. This is also one kind of machine learning model. And now, as of now, we develop these many models. So now I want to check that RMSE value and R-square value of the each and every model. So from that RMSE value and R-square value, I can able to justify that which model is the best one. Suppose one model having the highest RMSE value among the all remaining one. So I can say that that model is the best best machine learning model. Okay. So this is the code for calculating the R-square value and RMSE value for each and every model. Okay. So you see, among all, you check it R-square value, which is having the highest R-square value. So polynomial regressor, it is having a 0.97. And the next one actually 0.96 KNN regress also somehow little bit good. And here also RMSE value, it is actually 0.35, but KNN regressor also 0.047. So among all linear regression actually it is showing the worst performance, that is 0.53. But polynomial regression 0.97. Sometimes actually a Gaussian regressor also it is not showing best one. So it is around value 0.94. So we cannot say that which model is the best. So we have to develop all the models. So based on your data, so we have to cross check that which model. So but you want to stick on the particular model. Suppose I want to stick on only on the decision tree regression model. How to change the sensitivity parameters? I already told. So there is a lot of sensitivity parameters are available in the decision tree. So this is the default. As of now, I was conducted only default sensitivity parameters. So if you change that n estimators, if you change the splitting ratio, if you change that leaf numbers, if you change with that, you can improve the performance of the decision tree regression model. That can be possible. Okay, even Gaussian cross regression it is showing 0.94. But if you want to improve this performance, you can conduct the sensitivity analysis for this particular model. Okay, so what I'm actually, so that is actually very long topic. So that's why I'm not discussing about the complete sensitivity analysis of each and every model. So I just giving some overview of that all the models. So okay, among all these, how many machine learning models are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So among 13 machine learning models, so polynomial regression model showing the better performance, that is the 0.97. So I was developing. So how to get it, all these things. So the data I want to export. So for exporting this one, so this is for printing the data. It will be stored in the Excel file. So now predicted values were stored over here. And now calculated RMSE values also we can able to store it. Okay, so finally you want to store in the Google Drive. So if you click over here, automatically this entire predicted data will be stored in the Google Drive. So it is like customized codes. These are the customized codes. So wait, RMSE is not coming. Wait. Yeah, now it is. Now I want to extract that calculated RMS RSS data, so I can download this one. So this is the calculated one. So no need to do the Excel calculation and all. Code itself is generating that all model performance, R square value and RMS value. Okay, and predicted data I want to download, means this is the predicted already exported. You can able to export. You can download it. So this all the model 13 models are developed, So this is the comparison. So finally we can able to make the plots for the actual versus predicted. How LR means linear regressor and PR means polynomial regressor. This is the decision tree. This is the random forest, Gaussian process regressor, and support vector regressor and KNN. And this is the QR, quantile regressor, ridge regressor, lasso regressor, Bayesian regressor, and elastonet, and this is the gradient boosting regressor. So for all developed 13 models, actual versus predicted, you can get it. And this data actually normalized data. So earlier what we are doing, so we are preparing the data so that we are doing the normalization, we are conducting the randomization. So this normalized data value is only predicting. So now we want to get that exact value, you can denormalize it. So that is a formulation will be already available. So we can denormalize the data and we can get that predictor value. So now these models are developed. Now these models are developed. So what you can do? So this code, this entire code. So this is for actually my performance analysis I was conducting. But if you conduct any real-time application like any unknown data, so like vibration data or the whenever you conducting the machining operation, vibration data will be generating, and various cutting parameters. You want to check that machinability, and whenever you're conducting the wear analysis, and we are getting the wear data. So all that data we can dump over here, and we can get the models. So these models actually we can deploy into the any of the microprocessor and IoT system, and we can pass that unknown parameter, and it can able to sense the data. So likewise we can do. So this is actually these kind of models will be for only regression model. So I'm not to perform for classification data. This is for only regression model. Why? Because my data was only numeric data. That's why I was performing only a regressor model. So all these machine learning models are regressor only. Similarly, classification data, so classification models also available. What we are discussing, decision tree, random forest, there is also classification data will be feasible, and select SVR system support vector SVM models support vector mission. It is available for regressor. It is available for classification also. Like we have a similar kind of code we can develop. Instead of the regressor, we can use that classification syntax we can use, and we can run the model. So using these machine learning models, we can able to predict the data. But this is for only classification and regressor. But when you want to predict that image data and all, so image data and all, it is not useful using this model. We can go with that uh, convolution neural network CNN models we have to use, or else any of the machine learning models also, advanced optimized machine learning models also we can able to predict. So convolution neural network model, deep learning models, and we can able to predict the using that model we can able to predict the image data, and similarly using that. Similarly, using that vibration data and speech recognition data also, deep learning networks, so we have a certain codes are available, and even these kind of machine learning models also we can able to predict. One thing, either we can directly image data we can able to predict with the help of convolution neural network, or else what we can do, we can convert into we can process that image data, and we can convert it to numeric data. That numeric data we can able to predict by the help of this model. So that can be possible. So this is about complete case study. So what I'm telling is, so this already customized data will be there. If you have any experimental data, so simply we can dump over here. So we just what you have to do, we just import the data from that your Excel sheet, and once that after that just copy path over here, and after that you just run the all the blocks, and you can get that model. But if you want to perform the sensitivity analysis of each and every model, this code is not suitable, so we need to customize this data. Okay, so that and all actually I will take, if possible, I'll take another session, so that is also will be helpful for how to do the sensitivity analysis for all the machine learning models. So I think for mechanical engineering data, so mostly like regression models only, so no need to conduct the sensitivity analysis. But if it is having the more complex data will be there, so for those models and all, we need to perform the sensitivity analysis. So hyperparametric tuning is required. Okay, so this is the complete about that modeling of material. So here what I'm doing is, here I have the phase change material information experimentation I was performed. So that that data was I was imported over here, and I conducted the machine learning models for all the data. So this is what complete information. I hope you can understand. So today topic is little bit very fast. Why? Because I have a huge content, so I don't have a time. So that's why all together are clubbed to here, and I just want to take that one case study also. So that's why a little bit fast only. I hope you guys understand. Okay. Any questions from the participants?
Sir, excellent FDP, sir.
Sir?
Hello.
Yes,
Sir,
sir.
excellent, sir.
Thank you, sir. Thank you, sir.
So many things, sir. Within the short period, we learned so many machine learning techniques, sir.
Okay, sir.
It's excellent. From our side, a small request, sir.
Sir, tell me, sir.
Please share that code file, sir. We will track
Sure.
it, sir.
Yeah, definitely. I will share in the group.
Also, if possible, that data set also, sir, if possible.
Yeah, sure.
And one more
Actually,
request,
Hmm.
tell me.
Actually, I have a third session also. From that, actually, I just want to discuss about computational fluid dynamics, CFD, some hands-on session is there. So there actually, I
Okay,
have to
sir.
cover that hybrid algorithm. So what are the computational data we have now? So that data, how to model with the help of the hybridization neural network. So you can get complete information about neural networks and machine learning and hybridization model, how to model. So using our experimental data, how to model everything you can get. So sure, I will share
Okay,
all
sir.
this. Yeah.
Sir, one more, sir. I think if you published any paper on this topic, please share that paper also, sir. We will compare this with this code and
Yeah.
we will check with the paper, and we will get some
Yeah.
idea
Already,
how to write a paper by using this machine learning technique.
yeah. Already published this data in renowned
Share in the
essay. So sure, I will share that publication details also.
Thank you so much, sir, for your valuable presentation. Thank you.
Thank you.
Okay, any questions from the participants? Hello, any questions from the participants?
Hello.
Yeah, ma'am.
Madam, tell me.
Sir, good evening, sir.
Good evening, ma'am.
Sir, how much data minimum is required to do this coding on the machine learning?
Yeah, ma'am. Actually, for neural networks and hybridized neural network, very limited data is enough. Actually, L27 data is also we can able to develop the model. But when it is comes to that machine learning model, at least 100 data points is needed for getting. As my observation, it may be right or wrong, I don't know. But machine learning, if you want to do the machine learning, so if to avoid the overfitting, to avoid the underfitting, so least 100 data points are required.
Is L27 can we do it, sir? What is that?
L27 actually is not fit for machine learning models. Actually, some fellows are actually publishing data with L27, but as per my understanding, that is not actually perfect data. It may be overfitting. So overfitting, well, exactly the points are matching. So it is not possible. So L27 it is not good for developing the machine learning model. So hope I think more than 100 data points only it will be well suitable. But if you want to still develop a model for L27 data, so I can prefer you can prefer some hybridized model. So like ANN genetic algorithm, ANN PSO algorithm, ANN TLB algorithm, like any bi-inspired algorithm combined with ANN, that models are actually good for that lower data.
Those files, okay, where we can get it, sir? I mean, with example, to do hybrid model. What you said, right?
Yeah, ma'am. Actually in third session, definitely I will discuss about that hybridization models. There actually I will discuss about the CFD models. Well, from the CFD, we are getting some data, So, using that data, how to model it using hybridization model. That is also, I'll take some hands-on session. I'll cover that topics also.
Okay, sir, please, sir. Because I would like to learn.
Yeah, definitely, ma'am. I will share
Thank you, sir.
every information. Yeah.
Any example code, if it is available now, sir, we can.
This code,
Make
I will share
I'd
in
like
this
to see
code,
how
ma'am.
you
I'll show
applied
you.
all the. Okay, sir. You have
Actually,
applied all the algorithms, like the 7, 8
yeah, ma'am.
models, modelings. All
Yeah.
modelings are applied. Yes, sir.
Whatever the data, what are the code I was developing. This is for customized code. So if you have any experimentation data, so easily compatible, ma'am. So no need that much coding knowledge and all. So simply you just extract the data, you just read it and copy paste, and after that run each and every. Sure, I will share this code in the group itself.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Any questions? Sir, I want to ask one question.
Yeah, sir.
Sir, you selected randomly some algorithms, no? Why you selected these algorithms? There are so many algorithms. Why you are
Yes, sir.
comparing the only particular these algorithms? Any reason for this?
No, sir. Actually, we have so many algorithms, but what are the chosen algorithms are no? These are the most popular algorithms. Recently, they are using, but every year some new algorithms are coming. So sometimes, like even machine learning, also some hybridization people are doing, like decision tree combined with genetic algorithm and what do you call polynomial regression combined with teacher learning based algorithm. Like so they are keep on updating their codes, but this is actually basic only. So for basic understanding only I'm discussing this thing, and you can do that hybridization with these things also, so not a problem. So for most popular algorithms only I just explained, but we have so many algorithms, even 20-30 algorithms also available, but I'm not covering all these algorithms, sir. So for understanding only I'm discussing these things.
No, if we do any experimentation, if compare with these algorithms are enough for publishing papers, or
Yeah, sir, this is more than enough. Actually, if you see any paper now, so mostly people will supposed to compare only 2 to 3 algorithms hardly. But if you compare all these 13 algorithms, your paper will be very high, very high. It will be published in very high reputation journals. That too in mechanical. I don't know about CSE, but for mechanical engineers, actually this is good enough.
And coming to the deep learning, these
Ah.
deep learning algorithms are not applicable for this experimental data.
Yes, that is also applicable, sir. But the thing is that deep learning, we need a lot of time, sir. So it takes a lot of time. Why? Because we are increasing that number of hidden layers. So it is sometimes we can conduct with 10 hidden layers, and sometimes we can conduct with 20 hidden layers. It takes a lot of time. So if your data was fit for machine learning models, we can okay. Otherwise, what we can do, we have to go with the deep learning and hybridized neural networks only. We can prefer. So based on data, sir. So if data was very good enough, like it is not that much non-linear, it is linear form only, then even these machine learning models are enough. But heavily non-linear means sometimes machine learning is not able to predict. At the time, we have to go with the deep learning models, and we need to go with that hybridization models, sir.
Sir, they are coming to image based. Image based means completely will go for deep learning only.
Yeah, sir. Actually, sir, thing is that if you go with that image processing, so one image actually gives a lot of pixel information.
Okay.
So for predicting the perfect image, so we have lots of images, like sometimes 1,000 images are needed. Okay, at the time, so every time I want to convert into pixel data, every time this huge data I cannot dump into this machine learning model. So there is a separate algorithms are available for image processing. So convolution neural networks are available, deep learning neural networks are available. So for that, actually directly image itself, it will able to predict it. It itself, it will be converted. So it is not a problem for images. Even speech also, if you want to convert that speech into numeric data by decoding, that is also it takes a lot of data. So for speech recognition and all, it takes a lot of data. So that data, if you convert into numeric and develop the model, it is not easy task. For the speech recognition also, there is a separate libraries are available in the pandas, Keras and pandas, and like they're already having. So we can able to predict it directly. So separate algorithms are available, sir.
And also one more thing, I request you to provide some libraries which are important to machine learning algorithms. Can you provide that libraries?
Yeah, sir. Actually, I have a standard book for you. So I will share in that group itself. So if you read that textbook now, you will get a complete information about machine learning models.
Okay, we can read, but from your experience,
Okay,
maybe
okay.
you
Yeah, yeah.
find some libraries are very important.
Yeah.
That
I have
means
some information regarding my research relevant topics. So I will share those informations. I'll share in the group.
you are that file, no, that is Google Colab. Is there any software is good for the machine learning algorithms? Only
No, sir. Actually, in the Python, we have a lots of platforms are available, sir. Spider is there, like normal, everything is there. But Google Colab, best thing is that wherever you can do, so you can do it, sir. So not, it's not a problem. So simple. For our case, actually, it is Google Colab is enough. But if you want to run in offline means Google Colab is not fit. So at the time we have to, IDM softwares are available and like Spider softwares are available for compiling the Python. Anyhow, these machine learning and all, we are going with the Python only. But sometimes actually these machine learning model without, we doesn't have any coding knowledge. So some kind of softwares are available, like Veka software is there, and these data is already having some graphical user interference is there. So simply you can extract the data and you just select that particular model and it will automatically predict the data. So that's all. So no need to conduct all this coding knowledge and all. So that is actually user friendly softwares are available. I will suggest those kind of softwares also for particularly for mechanical engineers.
Sir, and one more thing I want to suggest, you are mostly focus on the that what is the part your experimental data.
Yes, sir.
Instead of that, can you focus on some machine learning algorithms? Yesterday's session also you mostly focused on the theory part only. After that,
Okay.
machine learning algorithms you completed within 20 minutes.
Okay.
Please, next session only you focus on the hands-on practice on machine learning algorithms.
Yeah. Actually, this session, what happened? I just want to explore some new advanced topic like 3D printed face change materials. So that is very innovative idea.
Yes, sir.
So
Yes, sir.
nowadays,
It is workable. Yeah, I can understand, but you can speed up these things and you can focus on the learning algorithms. No? That would be better. And the title of FDP, I meant to say, that is the reason.
Yeah, sure.
Thank
In
you,
the
sir.
coming session, definitely I will focus on more on these hands-on sessions. Okay.
Yes. So, any questions from the participants? Otherwise, we conclude the session.
Hello.
Ma'am, tell me, ma'am.
Thank you very much, sir.
Okay, ma'am. Thank
For
you.
the so I'm this Devi. I am giving the vote of thanks. Thank you very much, Ravi Kumar sir, for the insightful and thought-provoking presentation on phase change materials and 3D printing of phase change materials, applications of machine learning algorithm concepts. Your expertise and depth of knowledge and are provided with a great understanding of PCM composite materials, 3D printing of PCM materials, and machine learning algorithms, and have certainly enriched our program. We greatly appreciate the time and effort you have given. You have put into our sharing your valuable insights with us. Your contribution has undoubtedly sparked new ideas and perspectives that will your perspectives that will benefit all of us, and we will continue to explore the role of artificial intelligence in engineering applications. I thank you once again, sir, being
Thank
with
you so
us
much.
today and your exceptional contribution to our faculty development program, sir. Thank you.
Thank you.
We are ending the session. Thank you all. Thank you, the participants.